So for my project, I'm looking at if the largest changes in climate correspond to the largest drivers. Yeah, just go through my abstract to start, kind of go into what my research was. I looked at a bunch of research papers from the PETM, looked at some carbon data, looked at a bunch of temperatures in order to kind of map out what was happening during this event. I did this in order to kind of have a understanding of the past and during a significant time period in our planet's past with regard to mass extinctions and climate change, and kind of looked at if current trends with regards to climate change, if history is just repeating itself, and what we can do in order to not go through another event like this. Yeah, so to start out, I'm going to give a brief introduction to the PETM. We're going to look at some statistical data regarding the event, some ramifications of it, and then I'm just going to go through the same thing with current climate change. I'm going to connect the two between current climate change and PETM. I'm going to look at some summary and conclusions. I'll go over some of my further work that I hope to do in the future, and then I'll show you my references. Yeah, so briefly, the PETM is short for the Paleocene Eocene thermal maximum. It occurred around 56 million years ago, and it was where the planet warmed by an average of about 5 degrees Celsius over the span of 20,000 years. This event is considered to be the best model for modern climate change, and it's also responsible for the largest deep sea extinction in the last 90 million years, in part due to ocean acidification and a rise in temperatures. The scientists are still unsure of the exact cause of the PETM, but it's expected that some of the causes were ultimately because of methane gas releases and an increase in volcanic activity. During this event, anywhere from 3,000 to 7,000 gigatons of carbon was ultimately pumped into the atmosphere. This happened over the span of those 20,000 years, which roughly equates to about 0.3 gigatons to 1.3 gigatons of carbon emitted per year. This ultimately, so it's going to lead to ocean acidification, but before I got into that, I wanted to go through kind of what ocean acidification is. In short, it's in a natural process, carbon is dissolved by the ocean. This is a natural occurring process, so it's fine in and of itself. However, too much dissolved carbon can lead to a more acidic ocean and lower the pH value. Whenever this happens, it ultimately reduces the amount of carbonate ions in the ocean, which carbonate is needed for various sea creatures to build shells. And then more acidic water causes these shells to dissolve, so creatures that are at the bottom of the food chain cannot survive, which disrupts the food chain. So yeah, ocean acidification with regards to PETM, basically the sudden extensive increase in this atmospheric carbon, it resulted in ocean acidification. During this event, pH levels ultimately dropped 0.3 pH units, and this caused benthic forams, which are single-celled organisms. About 50% of them went extinct during this time period. This created a type of ripple effect through the food chain that impacted organisms at the ocean surface. For example, coastal oceans saw an unprecedented rise in dinoflagellates, which is just known as red tide. The emergence of these organisms is ultimately a sign of environmental stress. And then also plankton groups moved to higher latitudes in order to escape the stresses of their environment. And so, yeah, ocean temperatures ultimately rose to unprecedented levels during the PETM. Overall, there was an increase of around 6 to 8 degrees Celsius in ocean temperatures. Higher latitudes saw the most drastic increase, with like Antarctic ocean temperatures reaching around 20 degrees Celsius. Lower latitudes became virtually uninhabitable as temperatures reached around 36 degrees Celsius in the ocean. Deep sea ocean temperatures also rose to unprecedented levels as they got to about 14 degrees Celsius, which at that point it created something called hypoxia, which hypoxia is where warm water, which has lower oxygen levels, and so therefore, because of the lack of oxygen, organisms cannot respirate, so they can't breathe. And this is so ocean acidification paired with the rise in ocean temperatures ultimately led to a deep sea die-off of various organisms, and that was with the impact. Both of these kind of came as one giant storm, and it caused the largest deep sea die-off organisms in the last 90 million years. And then the PETM it's currently being used to study the potential ramifications of modern climate change, because if we can understand how ecosystems react during the PETM, we can have a better understanding of how they will react to an uptick of carbon in the future. Before I get into modern climate change, Current climate change is known as anthropogenic climate change, and I just wanted to go through that and what that was. So anthropogenic climate change, in short, is the belief that humans are responsible for the current changes in climate. This happens through a number of ways, through the burning of fossil fuels that result in excess atmospheric carbon. You have deforestation, and we also raise livestock, which do give off methane gas. In this, I'm just going to compare the current atmospheric carbon levels, ocean acidification levels, and temperature to that of the PETM in order to help draw comparisons between the two. So as you can see from the graph, there's a very strong positive correlation between the output in atmospheric carbon and CO2 emissions. Current projections indicate that 3,000 gigatons, which if you can remember was the lowest threshold during the PETM, current projections indicate that we will reach this by the year 2159, and 7,000 gigatons, which is the highest threshold of carbon emitted during the PETM. Current projections indicate we will reach that by 2278. For reference, humans have emitted 1,500 gigatons of carbon as of 2016. What took the PETM ultimately tens of thousands of years, it's only going to take us a few hundred years to replicate. So we're moving at an unprecedented rate of carbon emissions in our environment, which ultimately leads to other effects that I'll get into in a minute. To put those years into perspective, the year 2059 is only 159 years away. And 159 years ago, we were in year 2 of the Civil War. The year 2278, it's 257 years away, and 257 years ago, the US of A didn't even exist. It wasn't a country yet. We were still the 13 colonies, and we were still occupied by Great Britain. I really aimed to, with these numbers, I just wanted to show, like, these may seem like they're really far out there to you and me, but from a historical standpoint of the world and the totality of all of history, it's really not that amount of time. And we're only a few hundred ways from entering another PETM type event. So yeah, based on this graph, you can see that there's a clear inverse relationship between dissolved CO2 and ocean pH levels. In short, the more CO2 that gets dissolved by the ocean, the more acidic the ocean ultimately becomes. Ocean levels overall have dropped from around 8.2 to 8.1 pH units, which correlates to about a 25% increase in ocean acidity. By 2100, projections indicate that ocean acidity will drop another 0.3 pH units to around 7.8, which, for reference, a drop in 0.3 pH units, it took the that was the total drop in pH during the PETM. It took it tens of thousands of years to complete that total drop, and it'll take us about 100. So just to pair it with our carbon emissions, with regard to ocean acidification, we're seeing an unprecedented rate. And then this also correlates with ocean temperatures. The ocean overall has absorbed about 93% of excess heat from carbon emissions since the 1970s. This has resulted in global sea temperatures to have risen by about 0.13 degrees Celsius per decade over the last century. The deep ocean has also been affected by this, as 1/3 of that excess heat is absorbed in the deep ocean. We're projected to see about an increase of 1 to 4 degrees Celsius in ocean temperatures in the next 100 years. With that lower threshold of about 1 degree Celsius, it would take us about 600 years to reach PETM levels, and then with the higher threshold of 4 degrees Celsius, it would take us about 150 to reach PETM levels. So kind of going the same trends that we've been seeing so far. What took the PETM tens of thousands of years to complete, we're on pace to take anywhere from 150 to 600 years. Also, with ocean temperatures, we're seeing the greatest ocean warming is seen in the southern hemisphere. Basically, the ocean is really good at absorbing excess heat. And to show this, think about this. If we take the amount of all excess heat since 1950 that has been absorbed by the ocean, and instead we just put it into the atmosphere, the Earth would have seen a rise in global temperatures of 36 degrees Celsius. So the ocean is almost giving us like a buffer of climate change, if you will. It's really protecting us. However, this has a lot of negative ramifications that will come back to bite us in the future. For example, coral bleaching. Coral polyps, they ultimately have algae that live inside their tissues. And if ocean water becomes either too acidic or too warm, these algae become stressed and they ultimately leave the coral. This algae provides about 90% of the coral pulp's energy, and with its main energy source gone, coral turns a white color, hence the phrase bleaching. If the acidity and temperature of the water is not returned to normal, then the coral will ultimately die. The Great Barrier Reef is currently undergoing coral bleaching, and since about 1995 has lost about 50% of all of its corals. Ultimately, a loss of sea ice is a big deal as well. As you can see by the graph, the little blue outline you can see, that's looking at the sea ice extent. The sea ice is that range in the Arctic from 1981 to 2010. And as you can see, the pink is current. So as you can see, we're losing a lot of sea ice in the Arctic. In July of 1980, the Arctic sea ice covered an area of around 3.8 million square miles. Compare that to 20 years later, July 2020, the Arctic sea ice covered an area of around 2.8 million square miles. So we lost about 1 million square miles in the span of 20 years. It doesn't help that the Arctic is warming about twice as fast as the rest of the planet. And a study published in the Nature Climate Change indicates that during the summer months, the Arctic could lose all of their ice by the year 2035. To put that into reference, a toddler right now, when they graduate college, would not have, there would not be sea ice in the Arctic, which has other ramifications that we'll get into in a minute. But for now, I wanted to just provide this image to kind of visually show the amounts of sea ice that we're seeing. On the left, it was the Peterson Glacier, which is located in Alaska. The left is the Peterson Glacier back in 1901, and in the right is present day. And yeah, as you can see from the comparison of the two images, there's been a lot of ice lost. Ultimately, this has resulted in sea levels rise. This matters ultimately, especially to us in the United States, as 40% of the United States population lives in an area that is vulnerable to sea level rise. And as you can see from the figure on the left, from 1880 to 2020, there's been a consistent upwards increase in rising sea levels. And then from this, looking at a lot of visuals, I think it's best to look at visuals for sea level rise. The New York Times did a study. If you look at the upper image on the left, it shows India, and so the upper image on the left, the right image of that, that's a projection for 2050. And as you can see, a large part of Mumbai is projected to be underwater. Especially with India, this is a problem given that India is the second most populous country in the world with over 1 billion people. It would cause mass movement, mass relocation, and probably mass loss of life. And then if you look over here, top right to Vietnam, almost all of Vietnam is just going to disappear by 2050, according to the projection. Bottom left, we have Shanghai. And as you can see from the right image in the bottom left, most of Shanghai will be underwater, which same thing as India. China is the most populous country. And losing Shanghai would cause unprecedented problems for the country and for the world as a whole. Yeah, to go along with that, bottom right, Egypt, a good part of mainland Egypt will be underwater by the year 2050, which are all very concerning trends. Yeah, so from here, we can ultimately conclude that modern anthropogenic climate change is accelerating at an unprecedented rate. Given that the PETM took tens of thousands of years to be responsible for the deepest max sea extinction, it's very troubling. That's only going to take a few hundred years for us to replicate these same numbers that resulted in this mass extinction. Yeah, and so with regards to future work, what I really want to do is I want to research the ramifications of this anthropogenic climate change on various living organisms to see how organisms will adapt and ultimately recover from this, and if they will, or if it will result in another mass extinction. And then from there, I want to research the effectiveness of certain methods that aim to mitigate the effects of climate change. For example, renewables versus non-renewables, policy, electric vehicles, and even like sun dimming technology and things of that nature. And then from there, once I've kind of completed all this, I kind of just want to put everything together and create a website, just an educational website that people can use in order to kind of educate themselves on climate change, have a lot of interactive features and things like that. I think that'd be kind of cool to incorporate. And here are my references. And that's it. Thank you for your time.